Hi, welcome to everyone. Welcome to, to this talk. I'm Alessandro. From the Wolfram Research in the numerics group, and we are going to talk about plasticity, and in particular about the extension of the solid mechanics framework to account for nonlinear behavior of material like the elastoplastic deformation. You're going to find all this information in the new monograph that will be available in the uh, new version 15. In the monograph, you will find all that I will show in this talk with a lot more information about how to deal with plasticity, why we need plasticity, and how to model that for various example, plus some dedicated application example that I'm going to show you later. Um, Okay, so let's get back to the presentation. Okay, I will start with a brief introduction to plasticity, and then I'm going to show you how to modify the solid mechanics, the classical framework of the solid mechanics to account for the elastoplastic model. Then we're going to talk a little bit about some implementation details that may be really important to understand the following topics about yield criteria, linear hardening, and then how and why we see the effect of permanent deformation. And then we're going to move a little bit to a different view of plasticity, far from the metal plasticity, directly to the soil plasticity. Okay, so as I mentioned before, this is a completely new feature, as well as the monograph will be all available in the new version 15. Okay, so plasticity is the ability of the material to undergo permanent deformation. This came from microscopic sliding of the material, thinking about metals, about the different grains and the different metal phases. But we generally observe this from a microscopic point of view. We know that the material show different behavior depending on the strain. In particular, this is a stress strain curve of a metal, and we can observe different behavior. But with solid mechanics, we generally focus only on the linear elasticities, so a small part of the entire deformation curve. So to go beyond this limit, we need to understand how to describe the material. So this curve here is a general linear elastic curve where the slope is related to the Young modulus. And if we consider the yielding point of the material, after the yielding point, the material will no more describe the linear elasticity, but we need to account for a different description. And this is where plasticity comes to help. And in particular, we are going to see that we can model the for instance, starting with the perfect plasticity, once the material shows stress that by following the linear elasticity should be higher than the limit, the material is gonna yield. So it's basically gonna enable whatever deformation you need to, and the stress will remain to the yielding limit. Okay, to do that, we need an iterative approach because we need to solve the equilibrium, classical PD, so we can evaluate the stress, and we're gonna see if we are over the yielding limit. If the limit is okay, we can continue. The elastic solution is okay, but if, coming back to the previous slide, if the limit is higher than that, we need to come back to an acceptable solution throughout all the plastic solution that we're going to see in a minute, and then come back with a new plastic strain to the equilibrium equation. The problem is that the plastic strain, that is what the plastic flow computes, is a function of the stress, but the stress is itself a function of the strain. So this is a really nonlinear problem that needs to be solved with several iterations. Okay, let's start with an example. This is a beam directly from the monograph. Okay, this is a rectangular shaped beam where the left side is fixed and right side shows an applied displacement. So we're going to set the classical solid mechanics layer. So we have the mesh, we have variables, we have parameters. So Young modulus, Poisson ratio, and thickness. And of course, since we are representing a 2D model, we need to express if it's a plane stress or plane strain. And so we pick plane strain. We're going to set up the equation. As I mentioned before, we have the main solid mechanics equation and the boundary condition fixed to the left side and apply displacement on the right side. So as mentioned before, apply displacement, elastic solution, and we're going to find out this beautiful deformation. But this is not enough. We need to understand if we need to understand the stresses. So we're going to evaluate the strain, stress, and deformation stresses. Then let's pick. So we can see that the stress is really ugly to the fixed side. So we can pick a point in the region and evaluate the stress. Here, what we're going to find that the elastic solution is still is clearly on the elastic curve. It's elastic line, but it's the stress level is higher than the yield limits. So the solution is still valid for the elastic theory, but from a material point of view, this is not a valid solution. So we need to account for that. How? We can set up the elastoplastic variable. So we need to express the yield, the values of the yielding stress. Then we're going to evaluate it that all this region here is not safe, so it's over the limit, and then we're going to evaluate the solution. So we need an iterative approach here. So until the material is beyond the limit, we need to update the plastic strain with this function here that returns a set of update parameters accounting for the new plastic strain. So we're going to solve again the solution now with the new plastic strain, and this until the stress is the first come back to a good acceptable level. So in the end, we're going to find a different deformation. So these appear really similar since the displacement here is in both, but in the middle we can see some differences. But the real interesting difference came out when we evaluated stress. So now again, all the material is safe. And if you're going to evaluate them at the same point, the stress after accounting also for the plastic strain, so the elastoplastic solution, we are going to see that the red point here is at the final strain, the same total strain of the red point here, but the stress level is exactly on the perfect plasticity horizontal line. This is possible thanks to the plastic strain, so that we can also extract and evaluate it. And in fact, you're going to see that the plastic strain, so the material plasticize exactly in the area that we have seen to be over the limit. Clearly, this part here is due to the compression effect. This is due to the tensile effect. Okay, so some implementation details. How is that possible? So we need, as I mentioned before, we need an iterative approach. We need an yielding criteria. So it's a measure of the stress level. And generally, we need to compare something which is the stress tensor to a scalar measure. And for that, we need some conversion function that can be the von Mises stresses, the test stress criterion, or we are going to see other for the soil. Then we have the rule. The flow rule tells us how the elastoplastic, the plastic strain evolved. So this is an evolutionary equation that describes the increments of the plastic strain. And then we need some sort of hardening model, but I'm going to talk about that in a minute. Okay, so the flow rule is tell us how the plastic strain evolved. So this is an evolutionary equation that we can, in the end, we have no time here. This is evolution in terms of the previous step. So we can express that, since we have an iterative approach, we can express that as an algebraic system of equation, and we can solve it for each elastoplastic step to obtain the optimal values of the plastic strain. So solution of the plastic flow, come back to the elastic equilibrium, find the new values of the stress, and repeat that until the stress came back to the safe values. Okay, so this is the elastoplastic, the plastic strain computation, and then you solve again for the stress, and then you're gonna continue with this loop. The yielding criterion set the level where the material gonna start to yield. So it's an important measure, but this since the stress is a tensor, as I mentioned before, you need to convert that into a scalar measure. You can use von Mises stress, you can use stress K, which is the maximum differences between the principal stress components. And for instance, taking the same example of before of the beam, you can see that you can evaluate that it may appear really similar, but if you focus on the yielded region, you see some differences between the two criterion. Okay, the hardening describe if the material after the yielding can show changes in the response. So the curve is now aligned with a certain slope. The slope is the hardening modulus, and what we can see is that the yielding limit after the material is yielded can vary along this line. So we can see from this plot here, so material start yielding. Now ignore the elastic solution, so focus on the elastoplastic one, the green point. So now the yielding point is higher, so we unload, we start loading again. Now the material yield here. So all the strength across the material. So we can set an hardening modulus. Another example for the monograph is a plate with a hole in the center. We can model only a quarter due to symmetry condition. So we can apply, again, mesh variables parameters, equation with symmetry condition, displacement imposed to this side here. Bottom side can slide horizontally. This side can slide vertically. So in the end, we are going to see this beautiful deformation, and then we can once again evaluate the stress and strain. And all this red region here is beyond elasticity. So we need again to compute the elastoplastic solution. So new stress. Let's extract the stress in this point here near to the hole. And what we can see is a clear differences between the predicted elastic solution and the final elastoplastic solution that now is on the hardening line. Okay, coming back to the same animation, we can notice a different effect. So let's start with a load. So we load the material is gonna yield along the hardening curve. Then we unload the material. Have a look at that. Now the material move along a line which shares the same slope of this line here. So recover some strain from this line here, or this strain is recovered. This is the elastic contribution of the material. Let's think about a metal object like a clip or a fork. You can try to bend the fork and you can see some sort of flexion, but if you increase the load on the fork, at some point you're going to see that the fork show you a permanent deformation. And this is exactly what we can see here. So the material is beyond the limit, it starts showing some permanent deformation, which are the plastic strain. And in the end, you can see a deformation also if you remove all the load. Okay, and a second important point here that when you start reloading the material, so the permanent deformation remains, you move along the same hardening, with the same hardening slope, you're going to unload the material. Now the permanent deformation is increased because the material account also for what happened in the previous load. And this is why we talk about load history, in the sense that the actual state is a function of the previous loading step. Okay, so how we can observe that? So let's take the same example of the beam of before, so rectangular beam. Once again, the left side is fixed, right side show an imposed displacement. So again, mesh variables, parameters, yielding stress, equation, and the elastic deformation, okay? Then we can evaluate the permanent deformation. So we have so we know that the material is gonna yield in this region. So once again, solve for the elastoplastic problem. Okay, so have a look here. The displacement is still delta, so it's the impulse displacement, but we're going to perform another final step. So we solve the same problem with the same parameters. So update parts here contains all the information about plasticity, basically the plastic strain and some other important variables for plasticity, but the equation are the same, but the load, the applied displacement is now 0. So we can extract displacement, copy the deformed mesh, and what you can see in the end is that the so elastoplastic, elastic deformation, we've seen that before, but now there is a deformation, a final deformation. So with the black one, we have no load, but still it's deformation. Why? This is all related to the plastic frame that we can extract at this point. We can once again describe some line, which exactly this line, so elastic line, elastoplastic curve, and then we are going to unload the material. We are going to come back here. So point 3, the stress is 0, but the deformation is not 0. And this is exactly the permanent deformation. Okay, so now we always think about plasticity as something related to metals, but that not all. Also, soils may show an elastoplastic behavior. In particular, response related to the, in this case, mostly related to the shear. All this information can again be found into the plasticity monograph. So let's take this example here. This is a solid block of a generic soil where we want to construct a footing strip. So we need to account for the load. In particular, let's have a look at the section of that block. We can model only half of that due to the symmetry condition. So we have a sliding condition here on the side. There's both sides, symmetry condition and fixing condition to the bottom region due to contact with a generic hard soil. And then we have the footing here that we can express as some generic load. And what we want to know is that if this soil is able to carry out all the load. To do that, once again, let's construct a mesh. Let's define variables parameter equation that now account for the symmetry condition. And also for the boundary load of the footing. So all the area here of the footing is represented by an imposed load. What we can see is the classical elastic deformation. So we see this settlement here, but we want to know if we can accept that or not. How? Strain, stresses, once again. Now, for soil plasticity, the hardening, the yielding criterion may be a little bit different. But don't be scared about this formula. These are only different ways of reduce the multidimensionality of the stress tensor to a scalar values. So yeah, these are all function of the stress tensor plus some scalar value, scalar coefficient that are the elastoplastic coefficient or material properties that you need to know about your material. So let's in fact define some criterion. In particular, we are going to compare to these two different criterions. It can be shown that under certain assumption, they may be converted once into another by accounting for the right conversion of the coefficient. Okay, let's extract some, as I said before, some these are all auxiliary variables related to the stress tensor. So you can think about that as a different scalar measure related to the stress, like the different like the Bermuda stresses. Okay, so we can define the more column criterion, the Duger-Prager criterion, and we can compare that. Have a look at this plot here. You can see that the material shows all the soil appears to be safe, the green one, but clearly under the footing, we can see that the material is mostly not safe. And in particular, the brown one, the Duker plugger, is shows a larger area of probable yielding of the material. So what we can do, we can once again set up the different criterion for the. So we need to tell the we need to set up a material parameter and also the new criterion. We can do more column, we can do Duker Prager, and then we can observe the final deformation. Now, don't be scared by this larger, very large deformation. Clearly, the deformation here is scaled by a factor. I think this is a factor of 20 times, but what I want to show you is that there is a clear difference about the settlement here under the footing. So following the Duker-Pagan criteria, we can clearly say that this material may not be safe, the soil may not be safe due to this imposed load. While with the Morecolumn criterion and its elastoplastic evolution, the difference may be smaller than the last one, but there is still some difference. And for soil plasticity, is also interesting not only to extract stress strain, but also to evaluating the failure lines. So by extracting the principal stress direction, we can observe the maximum compressive state, which is the maximum, is the minimum of the smaller principal stresses, because we are still accounting for principal stresses ordinary with tensile positive, but we can see that the compression is really, really high near to the footing. This is clear because we are compressing the soil and propagates along the vertical direction here, but due to the lateral boundary condition, the compression tries to push all the sides of the material. And it's also interesting to extract the failure lines, which are lines connecting the principal, the first principal and the last principal stress direction. And generally, depending on the criterion, but for the more column, you have this more column angle, which give you a factor to modulate this line. And what we can see is that the line here show that the lines where the material is gonna fail, and also how the material is gonna fail. It's really easy for soil to think about the sledding of a certain portion of the soil. And the color map in the background show the maximum shear. So following this criterion, the material is really gonna fail here, where the shear is really high, also following that lines. Okay, so in conclusion, we have seen that we introduce a lot of example and a lot of information about plasticity. We can finally model elastoplastic materials, so going beyond the elastic limit. We can not only reproduce the hardening, linear hardening, perfect plasticity. We can compute final permanent deformation, so no load, only the plasticization effect. We can have different hardening criterion from the one related to metals directly into the soil. We can evaluate the final plastic strain, and we can also use all this information to evaluate it if the material is safe or not by failure criteria based on the elastoplastic criteria. So if the material is still in elasticity, it can recover all the deformation without any danger. Okay, and we are going to find not only all the information into the monograph, but also two interesting application examples that we are going in the new version. So on the right side, you can see it is related to a rod for slide surgery, when the surgeon needs to bend this rod to and model it to the patient's spine curvature, and for that it may be interesting for for the production of the right tool for that, or to optimize the surgeon to have a look at what happened with this material that are generally metal alloyed, showing really interesting plastic capability. That one is again for the slope failure. Let me see if I can show Okay, that this is a slope varying example similar to the strip footing one, but now you're gonna apply a load and see basically if the slope is gonna fail or not for that load. Okay, so with that, thanks you all to attend this talk. Now I'm gonna see if there are any questions. Okay, so okay, first question. Rather than specify an iteration limit, is it possible to prescribe a conversion criterion? An iteration limit alone may not guarantee a conversion solution. Yes, yes, of course, this is possible. Now we implemented, so we have different criterion implemented, but you can set that. You can set as another thing there, and you can set another condition manually by evaluating the difference between the displacement and the displacement at the previous step. You can also evaluate in stress, but of course you can set. It's important to specify a non-associated plastic flow. In some mechanic, associated plastic flow can give unrealistic egg dilatation, which can impact on the results by inflating confining pressure. Yes, yes, that's true, and that's you. So it's we are gonna see. I don't think in this version it may be possible. So the framework is ready for that, but we need to make sure that everything can go in safely go into the computation due to how we deal so with the numerical artifacts and how we extract information um, to the plastic to the elastoplastic step. But in the monograph into the implementation details section, you're gonna find more details about that and also how to better declare and configure the plastic flow criterion.